All right, fantastic. All right, let's just jump into it then real quick. So my name's Brennan. What I've got to share today is some results of investigations we've been doing at the Geological Survey into understanding how, when and why we get mineralised hard rock, very felsic peralkaline volcanics in the Mesozoic that have produced bulk rock chemistries of up to 2% zirconium and make things like the Toongai Chacolite, which form the core of the Dubbo Zirconia project that ASM are running. I guess up until that sort of economic angle came in, not a lot of people were interested in these rocks. But since that point, there's been a bit of work to be done to put them into their proper context in the evolution of the Tasmanites. So we do need to just quickly acknowledge that this work is done as a part of an ARC linkage project that the GeoSurvey is a major contributor to, and that we've had partners on this journey, specifically the University of Adelaide, University of Queensland and ANU, and also I'd like to extend thanks to ASM because they gave us access to their tenements and their drill cores in order to actually carry out this work. So just going to frame, I suppose, the rest of the talk just with a quick introduction and just kind of highlighting some key questions. So we're talking about hard rock, igneous-hosted rare earth element and high fuel strength element mineralisation. This is primary igneous mineralisation. We're not talking necessarily about secondary or weathering products of these types of rocks. But if you can have a magma that can crystallise an ore deposit at percent grades of rare earth elements and other high fuel strength elements, then well, how can that happen? What sols of magnetism can actually achieve this? And if you were going to look for these, how would you identify that you were in the right area? What's the sorts of what makes a rock prospective? And how does this fit in with the context of New South Wales geology? So what is the temporal, the age of when do these rocks come in? How does this link to the tectonic evolution of New South Wales? And armed with that knowledge, where else might we be able to look for some more? So we get the first part of the talk. I've used a lot of terms already. We're going to get into unpacking some of what those terms are, what they mean, and to have a quick little discussion about what these rocks are. So the term peralkaline is one I've thrown out a lot already. What does it actually mean? Well, what we're talking about are silicate magmas with high abundance of alkali metals. Alkali metals in excess of aluminium in that magma, which means that those alkali metals can't be accommodated purely by crystallization of feldspar. That's the normal thing that happens in like an I-type system. All your sodium and your potassium, those form feldspars, and that's okay. But when there's not enough aluminium around, you can't do that. And when the alkali metals remain in solution in that magma during fractional crystallization, it changes the behavior of that magma. So in a peralkaline magma, most of the potassium will go into feldspars and along with some of the sodium, but you end up with a build-up of sodium generally in the melt, which is then accommodated in iron-rich minerals. So an indicator minerals that you might be dealing with a magma with this sort of chemical composition are sodic pyroxenes, such as aegerin, or sodic amphibole, such as arthitzinite. And if, depending on the level of silicon activity in the magma, you might start making sodic feldspathoids. Geochemical criteria for these sorts of rocks, they usually have a very high gallium to aluminium and iron to magnesium ratios. And that's just because they're very low degree partial melts of the magma, of the mantle. So when you melt the mantle by 1% or 2%, these little sweats that come off of it, they will be the first elements to enter the melt during melting will be the elements most ready to leave the mantle, the elements that were the least compatible, the least happy there in the first place. So they take the first bus out and they get into the melt, and so you end up with high ratios of gallium to aluminium and iron to magnesium because magnesium likes being in the mantle very much. You get very low titanium, chromium and calcium. This is indicative of the level of fractional crystallization that you typically see when these things make it to surface. They're intensely fractionated and that pulls out these sorts of elements on that journey. If you are looking at them in the field and you had a PXRF, zirconium would give you a good indication that you're looking at a peralkaline rock that's enriched in high fuel strength elements, because zirconium is just simply the most abundant. It'll give you the best reading. And they're also quite enriched in actinides. Petrogenesis for this, as discussed, they are very low degree partial melts of the mantle, but that's not enough. All the modelling, all the research that's been done and the experimental work that's been done for these magmas shows that simply melting the mantle isn't enough to generate something that's going to be economic something that's going to be able to reach that percentage grade of rare earth elements and high field strength elements. To achieve these sorts of grades, you need to have additional input of incompatible trace elements into your mantle source. And the mechanism that gets invoked for that is subduction-related metasomatism. So donation of incompatible trace elements into the mantle during subduction. So what does this mean, and why do we find these alkaline igneous rocks attractive as an exploration target compared to, for example, a carbonatite in the rare earth element space? I mean, almost all the rare earth elements in the world are provided by carbonatites. And there's two reasons. Is one, the other high fuel strength elements that you find in these alkaline igneous rocks like zirconium, tantalum, niobium, hafnium, they drive a lot of the value of that project. And additionally, the alkaline igneous rocks will have a higher proportion of heavy rare earth elements relative to carbonatites. This little graph here just shows the average bulk rock composition of alkaline igneous rocks compared to the bulk rock composition of the Mountain Pass carbonatite in the USA. And yeah, it just shows the drop off in heavy rare earth elements in that deposit. The geophysical criteria, as I said before, these things can be quite enriched in actinides, but enrichment is a relative term, depletion is a relative term. So whilst these rocks are always quite potassic, their level of actinides can vary, and if you have a very high amount of thorium or uranium in that rock, it's probably a good indication it's also concentrated other incompatible elements, so the ones you're after economically. So if you look at this in the geophysics and use a stretch of thorium divided by potassium, then rocks that have very low actinides but very high potassium will show up as blue, and red is for the inverse. And so this is a little clip here from central New South Wales and the radiometric stretch that our geophysicists made. You can see the very large, anyone who's been to Toongai or any field trips or anything will know that there's a very large peralkaline plug that sits immediately next to the deposit. And that's called, the common name for it is Dowd's Hill. And you can see it shows up in blue because it's peralkaline, it's Adrian bearing trachyte. It's very potassic, but it's very low in actinides and very low in basically everything else. It's a bit of a dud. But the deposit sits immediately off it, off the east, so the western margin, and it's very, very red. You see Toongai there, and the railway prospect as well that's nearby also shows up a bit like a light bulb. So the mineralogy, again, because these are dominated, they're so enriched by alkali metals, you get alkali mineralogy. So you get a lot of feldspars, you get alkali-rich feldspathoids, you get sodic amphiboles and pyroxenes we discussed earlier, and you get ore minerals. So the sorts of ore minerals that we're talking about can be as simple as zircon or bdelliite, and then it can get more complex, like the eudolite group minerals or EGMs that you see at Toongai, and you also see in some of the world equivalent resources, such as the Strange Lake Pluton in Canada, or the Ilmasak complex in Greenland. This is the major ore mineral and those things as well. And then your suite of phosphates as well as pyrochlorine, iobate. Secondary minerals, which can be very helpful because sometimes some of these primary ore minerals can be very difficult to treat. So the metallogeny improves if you have rare earth element bearing clays and carbonates. They can be quite easy to treat in comparison. So weathering can be a good thing in this case, and I think the Narrabri guys who are coming after me will have a lot more to say on that topic. Okay, so just now we've covered through this background information, we've defined these terms and we understand the type of magmas that we're actually discussing. I want to get into the next part, which is the real body of work that we've done in placing these into context into the evolution of the Tasmanides. So by the Mesozoic, the Tasmanides are pretty much assembled. The last major orogeny in the Hunter-Bowen orogeny, peak compression hour in 265 MA, that's finished, and we're into the late Triassic. Following the Hunter-Bowen orogeny, you have a decent amount of A-type magmatism in both the New England and a little bit in the Lachlan. For example, the Midway granite, with the Dolladilla prospect there, and the large body of A-type granites in the New England, such as the Brothers. And they all come in following the Hunter-Bowen orogeny around 235 million years. So if we're going to focus on the Mesozoic, because our best examples of mineralised peralkaline magmatism in the Mesozoic, we just want to focus on what's happening in the late Triassic. So there's two major episodes of magmatism that occur during the Mesozoic in New South Wales, and that shouldn't say the Mesozoic, that should say following the Hunter-Bowen, because that ignores all the I-type magnetism in the New England that's in Hunter Bowen. But these two major episodes, as I said, low volume late Triassic A-types that occur following the Hunter Bowen orogeny. And this is a pretty good tectonic setting if you want to generate mineralised peralkaline magnetism. And there's a really interesting paper there by the British Geological Survey, Catherine Goodenough, that details exactly this tectonic setting. It is a geodynamic end member for this style of mineralisation. And the more voluminous Jurassic volcanics that occur, that are associated with the opening of the Strat Basin. So the Garrawilla volcanics is the name we use in New South Wales. These are a large package of volcanics. They're rift-related volcanics at the basin of the Surat that opens in the Jurassic. So being able to tell the difference between these two packages of volcanics is very important, because one is related to the post-collisional melting and one is related to the rift melting at the opening of the Gab. So Triassic or Jurassic, well, traditionally all the rocks around Toongai and all the whole full field of felsic peralkaline rocks south of Dubbo have been considered to be Jurassic, based on some whole rock argon work and such that have been done a few decades ago. So I have gone through, one of the big outcomes of this work is we generated a lot of new geochronology. I originally anticipated that there might be multiple resolvable igneous suites in this area that are interfingered, but all the ages came out reasonably consistent. And we used a variety of methods there, both uranium, lead on apatite and zircon and argon. And yeah, we just kept getting the same ages around 210 to 220 MA. So this pretty conclusively or overwhelmingly demonstrates that this field of rocks is associated with that late Triassic melting following Hunter Bowen. And that's the prospective age. The Jurassic rocks associated with the Garrawillas, not so prospective. So if we apply this to New South Wales, this diagram's a little bit of a work in progress, so you can probably poke a few holes in it. I'm trying to think of a better way to draw it up. But essentially there's a couple of elements of this diagram I want to unpack because it's a part of the recipe of the mineral system of how you produce these sorts of mineralised volcanics. So the Lachlan origin has experienced a lot of subduction, all the way from the oceanic phase prior to accretion onto the side of Gondwana during the Benambra orogeny, through the Tabarabran and the Kinnimbulin orogenies, and then ultimately terminating after the Hunter Bowen orogeny, the Gympie terrain docks of New England. So there's a tremendously long period of subduction has occurred in the Eastern Australia and the Tasmanides. And as I mentioned before, it's a requirement to generate these hyper-enriched magmas that you have some other input or some donation of incompatible trace elements from an outside source, and it's almost always subduction related. So the mantle beneath the Lachlan is very fertile for this style of melting, and this is why you can see this in New South Wales and not necessarily in other parts of the Tasmanides, is because we have all the ingredients that we need here. We have the collision of the Hunter Bowen, the relaxation following the Hunter Bowen orogeny, is mostly accommodated by extension in the New England, and so the granites there are more voluminous. But you still get a little bit of extension in the Lachlan, and you get that triggers in very, very low degree partial melts of a very enriched lithospheric mantle that, once you fractionate it to the nth degree, can give you a rock with percentage grade zirconium and rare earth elements. So I've cut my own lunch a little bit on this slide, but I've pretty much said why the Lachlan is perspective. And what's interesting about the mantle underneath the Lachlan origin is that it remains more or less isotopically consistent throughout its life, following the Tabarabra and all the way up to the Hunter Bowen. So Tony Kemp's done a lot of work, and others have as well, but the bulk rock epsilon neodymium values for A-type magnetism through the Lachlan are around 2 or 3, and that's the same values that we get from Toongai. So obviously the contact between the Lachlan and the New England is obscured by the Gunnedah Basin where these rocks occur, and you wouldn't be quite sure if it was melting New England crust and coming up that crustal suture, or whether it's melting Lachlan crust and coming up that crustal suture. Well, what this would tell us is that it's melting mantle underneath the Lachlan, and again just feeds back into that story. And there's a side effect of this is it also means that this continuous history of subduction underneath the Lachlan means that A-type magnetism through the Lachlan at other periods of time, not just the Mesozoic, may have the same potential to melt this mantle and generate something economic. And a good example of that is the Narrabri granite, which is a post-Tabarabran granite. It's very strongly peralkaline, it's arabesonite bearing, and the weathering products of that granite are producing a clay-hosted resource, which Godolphin Resources are working on. So the Lachlan has the potential to provide these sorts of resources, but in a variety of different forms. So just to recap, the recipe for Mesozoic peralkaline resources in New South Wales, these peralkaline A-type intrusions and volcanics are from the late Triassic, and they need to be differentiated from the Jurassic rocks that are associated with the opening of the Surat Basin. The Lachlan origin is uniquely suited in the Tasmanites to be producing these sorts of resources because of its subduction and orogenic history. And after every orogenic event, there is A-type granites, A-type magmatism in the Lachlan, all of which has the potential to produce enriched peralkaline magmas. We can't know for sure, of course, that other orogenic belts in the Tasmanites haven't produced these magmas, but we do know that Lachlan ticks all the boxes, and we do know that no one has managed to find anything that looks particularly good outside the Lachlan. There are other peralkaline rocks in Eastern Australia, including a number in Queensland, the Peak Ranges, Mount Hedlow and Glasshouse Mountains, just to name probably the best examples of that. And there's a good compilation on this that David Purdy at the GSQ has done for peralkaline rocks in Queensland, but none of them seem to even get close to what we've got here in New South Wales. So if you were going to look for other Triassic volcanics in New South Wales that might be of the same age and might be the same system as what we now call the Bennelong Volcanic Suite, we formalised that name for these rocks south of Dubbo where Toongai is, where would you look for it? Well, the majority of the rocks in the PMIP, or the Permo-Mesozoic Igneous Province layer that we have in Minview, are these voluminous Garrawilla volcanics, most of which are interpreted from geophysics because they don't actually crop out. But there are others getting around that either have no dates or have a little bit of evidence that they might be of the age range that we're interested in. The best example is there's a series of ungrouped Mesozoic volcanics. Some of them just poke their head over onto the Dubbo 250k map sheet, which means the same people mapped the rocks at Dubbo where Toongai is, and they recognised that they were the same sorts of rocks. The descriptions that are in the mapping notes describe peralkaline, aegirine and arfvedsonite bearing phonolites and trachytes in the hills to the east of Mudgee. And that's kind of an interesting thing because that's hard yucca terrain. So unless you've really climbed all over and up and down it, there's peralkaline bodies up there that no one even knows exists. So that's an interesting thing. And there is a single shrimp age from one of these phonolites there that was done by Lance Black in, I think, 2008. And it came out at 231 MA. And that's exactly the age period we're looking at here, this post-Hunter Bowen. So I'd suggest that these rocks here in the hills east of Mudgee are definitely related to the same volcanic system and therefore have potential to be mineralised the same as what we see at Dubbo. There are also other rocks getting around. For example, the Bulga complex, which is a series of peralkaline plugs that intrude up near Malele. They've never even been dated. We don't know how old they are. And they've never been formally described either. There is one paper that a geologist by the name of Judith Bean did back in 1974, where she pulled apart the Garrawilla volcanics into its now constituent units. And yeah, the Bulga complex is one of those. And we don't know anything about it other than the fact that she described it as being incredibly sodic. So they're peralkaline plugs. The Glenrowan intrusions that are up there as well, that they're intercepted a lot in drill core from the coal companies doing drilling in the Gunnedah Basin. They're also described as being quite alkaline, but again, there's no geochronology on them, there's no formal descriptions, we don't actually know what they are. And there's potential for all sorts of little intrusive alkaline complexes as you go through the southern highlands of New South Wales, where there's other Mesozoic peralkaline things or highly alkaline things getting around. But some of those may actually be truly Jurassic and may actually belong to a different mineral system that we don't quite understand yet. They might not be in the same camp as what we have here at Dubbo. So that's all I've got for you today, and I think, yeah, happy to take any questions.